So let's talk about some applications of suffix trees. I won't discuss all that there are. I will point out to a book that's essentially full of applications of suffix trees. And hopefully that will convince you that these are really magic in a sense. For this section, again, just remember the suffix tree is actually stored like this as a compact trie, with the nodes storing the next character we compare, etc. But for explaining everything, we will use this human-readable version where the edge labels are spelled out as words. And I think I also, when it's convenient, I put the copy of the string into the leaves. There's a slight technicality that's not very important, but for some of the statements to be true, we assume that every internal node has a direct pointer to one of its leaves. And it could be, say, the leftmost in the subtree. So it's fine for this one. That would just be the parent pointer. But in principle, all right, in this example is too small. None of the internal nodes has only other internal nodes as children. But in principle, this can happen. So it could take a long time to go from a specific internal node to some of the leaves. But we assume there's a way to directly jump to one of them. It's easy to do this. We'll just rely on it. It doesn't blow up the space. It doesn't really change much. I want to mention it nevertheless. I'll sometimes abbreviate the ith suffix of the text like that, just to save some space in formulas. So it means starting at the ith position, it goes till n. So remember, the nth position in the text is the $sign. OK. Ready for the applications? Number one, we started this unit on text indexing, so we'd better see an application for text indexing. And that's indeed the easiest application of suffix trees. And the observation is just the following. If you have a pattern P that you would like to know whether or not or where it occurs in a given text, well, it occurs in the text exactly if this pattern is the prefix of a suffix. Then it occurs at a specific position inside the text. Now, the suffix tree gives us a convenient way to access all the suffixes. So we can just go ahead and check if this is the prefix of some suffix. It turns out this is exactly what tries are good at. We discussed that procedure informally last time, but here's it spelled out one more time. And I want to go a little slowly and through some examples, because this is an important application. What we have to do to check if there's any suffix for which our given pattern is a prefix is we have to walk down the trie following letters from our pattern. So for example, if our pattern is n, then we follow the first character that brings us here, reading the A, n, oops, and then we're actually stuck. There's no way to read the second n. So we follow a path with the label of our pattern until one of those three things happen, and then we know what to do. The first case is we're stuck. We would like to follow with a character out of a node, but there's no edge of that character. That's the case for n. It could also happen that we're inside of an edge. If you try to find BB, you would start here, read the first B, everything's fine, but then the edge continues with an A, but our pattern has a B, so we are again stuck, but in the middle of the edge. In both cases, the implication is that P does not occur anywhere in the text. If it would, there would have been a path in the trie, and we wouldn't be stuck. The other option is we continue reading, and then the pattern finishes, and we're still somewhere in the tree. So that happens if we read this. If we take this second example, we read A, N, A, and then we're at this node. And the pattern is gone. We run out of pattern. In that case, we know that this pattern does occur in the text, namely at all the positions in all the leaves in the subtree of the node that we reached. And if we stop reading inside an edge, we just walk down to the next node, and that's our node. So let's double check that this is true. Anna should occur at positions 1 and 3. Remember, we start counting at 0. So Anna is here, and 0, 1, 2, 3, it's also here. It's two overlapping occurrences of Anna. OK? All good? It turns out if your suffix tree is represented like this, these are the only two cases that can really happen. Because either you run out of pattern, or you can continue walking, or you're stuck. There's nothing really else that can happen. In the computerized version, if you implement the algorithm, there's a third case, because we store this as a compact trie, which means you skip over characters. So in that case, it can happen that, well, you run out of tree. You still have parts of the pattern to read, but you end up in a leaf. And you can't really continue from there. In that case, P doesn't occur because we assume that P doesn't contain the $sign. So if you could reach this leaf in that way, I guess you should check with the. It could be a prefix of the pattern, couldn't it? I'm not sure if this is correct. I think what you want to do, if you reach a leaf and you can't continue reading, you would have to do what you do in a compact trie. You check the characters you skipped. And then you would find out that the pattern is a prefix of the suffix your leaf represents, or it's not because there's a mismatch. And then in either case, you know what to do. So this means if you're finding the first match, the same setup we had for string matching in Unit 4, you can find this in, well, theta of length of p time. You go down one step for each character. And if you arrive at an internal node, there jumping to the leftmost node gives you one match. But it's the lexicographically smallest. It's not necessarily the first. So you can find one match in the tree. If you modify the assumption on the last slide, you get the first one. But as it's written here, it's you should say one match. You can find some match in the text if it occurs in this time, or you can find out that this pattern does not occur. So why this weird formulation? Why not say you can find the occurrences of the pattern in the text? It's a technicality. If the pattern occurs many, many times in the text, the output would consist of listing all those positions. I cannot do this in that time if there's more than p occurrences. There could be more than size of p occurrences, and I have to list them all, so there's no way to do this unless in this time that I stated. And then you would need extra time for doing this. You can report all occurrences by just doing a traversal of the tree where you get at the point where you ran out of pattern. You can list all the occurrences, but you need extra time for that. So if you want something that's bounded in the size of p, you can do the first so-and-so matches. OK? So once again, we can do the string matching problem, but from the text indexing perspective. If the text is given and fixed, we can once construct our suffix tree, and then for a pattern that we're given, we can walk down the tree along the pattern and find out where it occurs in the text or that it doesn't occur. Okay? That's the main application for text indexing in the classic sense, if you're finding exact matches in the string. And note again that this works irrespective. There's no word boundaries that enter in this. There's all suffixes stored, so you can search beginning at any position and you'll find any occurrences of that pattern. But we can also do a lot more with suffix trees. And you've already seen this problem, the longest repeated substring. Well, it's not now. You've seen the longest common substring. This is almost the same problem formulated for a single string, the longest repeated substring. You have a single text, and you'd like to find a substring of that text of length L, so that this same substring occurs at some other position in the same text. That's a repeated substring. Okay? It's very related to the longest common substring problem, as you'll see in a minute. And it's the same puzzling situation. How should you check all the possible substrings? There's just too many of them. So if you try any direct elementary approaches, it seems impossible to do this. There's actually an application for this that we might discuss in the next unit, if you find the problem too esoteric. It sounds hard to do this. But it turns out with a suffix tree, there's a simple and structured way to find these longest repeated substrings. And well, before you look at the details and the example, the intuition I want you to take from this is, if you have a repeated substring somewhere in the text, it occurs here and here, then there's two suffixes, namely starting at the beginning of the repetition, that begin with the same string. Those two suffixes are stored in the suffix tree. That's a suffix tree. So there will be some path to the first and some path to the second suffix. But because they start with the same string, their paths will be the same up to a certain point at which they split. So that means there's for sure this repeated part and at least two leaves below that. So there must be an internal node somewhere on this path, right? There's two paths that split at a point. They can only split at a node. So let's see an example in our banana band case. The smallest example here is just the A. So if we look at those two suffixes, their paths, maybe I should use different colors. The aban goes down here, and the an goes down here. They share this first edge, and voila, there is a node that has a path label A. And this is always the case whenever you have two suffixes that have a certain longest common prefix, the longest part that they share at the beginning, there will be an internal node with that path label. There has to be one because the paths split there. The longest repeated substring will for sure be one longest common prefix of two suffixes, because it has to occur somewhere in the text, so there will be the two suffixes that start at the beginning of the two occurrences. Those are your witnesses for this statement. So asking about longest repeated substrings is the same as asking about longest common prefixes of suffixes. It's even hard to pronounce. That's why people start to abbreviate things, which doesn't make it more understandable. But so this is a standard abbreviation. We'll use LCP for longest common prefix. There's no abbreviation for longest repeated substring. I think that's not used, LRS. Now, it turns out you can even restrict this a little bit. You can actually use adjacent leaves in the suffix tree instead of arbitrary ones. So for any internal node, you can find two leaves that are, okay, what do I mean by adjacent? Maybe I should say this first. This is a tree, and you can traverse it in depth-first order that walks along the tree. That would essentially imagine you walk on the outside of the tree all around. And on this walk, on the outside of the tree, you will walk past, you will visit each leaf exactly once when you turn around it. And that gives you an order of the leaves from left to right. Okay? If I cared to draw the tree a little differently, you could project these down so that they're actually next to each other. Then the edges would look a little weird. But other than that, there's no magic going on. Okay? So there's a natural left to right order on the leaves. And that means I can also speak of two adjacent leaves, ones that are on two positions next to each other in this ordering. So what this little statement says, for any internal node, I can find two adjacent leaves so that this is their longest common prefix. And we'll use that later, and I might explain it later again. But the reason is, for any internal node that we might have here, it has at least two edges, because it's a compact tree. There's no unary nodes. So you can follow two different paths from there. So you do one step where the paths split and walk, well, left and right, and then you follow inward edges as long as you can. So the left path follows only right edges after the first step. The right path follows only left edges after the first step. That will bring you to two leaves, and those are your two leaves for which that node's path label is the longest common prefix of those suffixes. We'll come back to that. For now, this is not as important, but I wanted to point it out at that stage. Coming back to longest repeated substrings, this statement helps us because it says a longest repeated substring must be found as the longest common prefix of some suffixes, and those are essentially the internal nodes in the suffix tree. Why does that help us? Because there's not so many of them. Remember these internal nodes in the suffix tree, the red guys? There are at most as many of those as we have leaves. Actually, one less. Because it's a tree without unary nodes. You can do this counting argument with slots downwards and slots upwards. Maybe that's something for the tutorials. So this narrows down from all possible substrings that we might initially have thought we might have to look at, down to just all nodes in the suffix tree. And there are not so many of them. We can actually afford to walk through all of them and ask for each of them, are you the longest repeated substring? And that's what we'll do. To find which one is the longest, in this tree, conceptually what we do is we walk down to each of the internal nodes. We find what is its path label ANN for this guy, and we take the length of this. That gives us all the repeated substrings, and we find just the longest of those. The way I described it sounds like we would have to recompute these path labels all the time, and that would be too expensive. But we don't have to. We can compute something called the string depth of nodes. And that's exactly the length of the path label to this node. And it happens in the compact tries to actually be the number we write into the nodes anyways. So if you implement the suffix trees with compact tries, you don't even have to do anything. But conceptually, we can walk around the tree and keep track of the current depth, and then go over the next edge and update it. So let's do this on this example briefly, maybe. The root always has string depth 0. There's no path to the root, so that's empty. The root is at depth 0. Now we would go to the leaves, but string depth is only interesting for internal nodes, so we come back. We do a depth first traversal, right? So we follow edges as long as we can, and if we reach a dead end, we go back to where we came. Now we follow the next edge. We know that this edge has 1 character. That's why the string depth increases to 1 at that stage. And if the edge had more characters, we would have more added to the current depth. So we can already assign this node the string depth 1. Now we follow again this path. There's a leaf, so we come back. We follow this path. There's 1 more, so this has 2 because there's 1 more. A leaf, again, this is a 3, and then we're done. Back to the root. That was the first path that we follow. Then here we have an interesting edge. BAN is 3, so here we get 3. No, just leaves left. This is a 1, this is a 2. That's how it goes. OK? You can easily do this in a traversal of the tree in linear time. And if you store it as a compact trie, you would actually have those numbers anyways. And then the second step is very simple. You go through all those nodes again and find the one with the largest number. So in this case, 3. So that would prove that the length of the longest repeated string is 3 in this case. And ban is one instance where this occurs. It's not unique. There's another node with depth 3. So there's another repeated substring of length 3, which is Anna, as we've seen. I thought we've seen in some example. But you can, yeah, it was part of the pattern matching. But you can check. Ban occurs twice, and Anna occurs twice too. And for Anna, there's this interesting feature that this definition allows. The 2 repeated parts, they're allowed to overlap, which is a little weird maybe. And you can twist the algorithm to avoid that in case you're interested in only the non-overlapping ones. All right. That was a little more complicated than the first application, but it wasn't too bad. And as you'll see, it's very close to this complicated problem that Don Knuth conjectured would not be solvable in linear time. So we'll now come to this problem. But to deal with it, we have to somehow change a little bit our tree. The longest repeated substring was fine. Well, I just claim it's similar to the longest common substring of several strings. You'll see in a moment why. So you would hope that we can solve this in the same way. But it doesn't quite work if you just build the suffix tree for each of the texts. We could build the suffix tree for each of the texts separately and then try to play with this, but I'm not aware of a way to make this work. The problem is that this longest common substring asks a question that needs information from all the strings at the same time. So what we need is a single data structure for all those strings. And that's what the generalized suffix trees are. What they do is you take all your strings, you add an end of word character, as we always did. The difference now is you add a different new character after each of the strings, so that they're different and you can distinguish them. And that gives you one long text. And from this one long text, you compute your suffix tree. Okay? One more time. You take the individual texts, the individual strings, you concatenate them, but between, at the boundary of the strings, you put a special marker, a new symbol in your alphabet that tells you now here's the end of one string and the next one starts. And you make those all unique so that you can tell which string starts at a given position. That gives you one long text, and you build the suffix tree on that. Okay? So essentially, the generalized suffix tree is the suffix tree for this text. Now, we can do a slight, well, cosmetic change. A suffix of this long text, there will be many suffixes that start in the middle of one of the strings. Then they continue till the end of this string. Then comes the $J, and then comes all the copies of the other strings. But we don't really need those. What we're interested in is only the part up to and including the first $. So what we'll do is, instead of writing just the position where the suffix starts, we'll conceptually stop at the first $, and we'll also translate from did I write this anywhere? The ordinary suffix tree would say you start at position I, and then there's your $J, the first $, and then all the other strings. Now, we would rather like in our leaves to store which string is this and where inside that string did the suffix start, as opposed to where in this concatenation. Okay, I think for the examples, this is rather an implementation detail. In the way we draw the trees on the slides with the edge labels, you can just assume that we stop at the first $sign. Okay, example for that. Maybe first. Here are 3 texts. So our long concatenated text would be this $1, A, B, C, A, $2, B, C, A, $3. And the suffixes of this long text would start at any of these positions and continue till the end. But as you'll see in the leaves, we stop at the first $sign because everything else behind that is not interesting. Other than that, this is just the suffix tree of this text. Ignore the green parts for now. It's just the suffix string of this longer text. Okay? So in principle, you can construct it in the same way. You could take the standard trie of all the suffixes and then compact it again. That's if you want to do it manually. The efficient way to do it, we'll see at the very end of this unit. So that's generalized suffix trees. We can take, with rather simple changes, we can use the suffix tree for a single text and apply it to several strings. And now we can talk about things that occur in the different texts. So now finally back to this motivation problem that got us started with suffix trees, the longest common substrings. How do we solve this? Okay, we can, maybe before I show you the solution, I can motivate a little bit why this is the way to go. As before, we can take the internal nodes of this suffix tree, and those represent repeated strings. Those represent strings that occur at least 2 positions in the long text. Now, those 2 positions, they could be entirely inside one of the texts, in which case it would be a repeated substring in that text, but not a common substring. Also, it could occur in 2 of the texts, but not in all 3. So we have to restrict our attention to those internal nodes that do have an occurrence in each of the strings. Okay? And we know where the occurrences are by looking at the dollar signs in the leaves below. So, for example, this node, it represents the string ABCA. That's the label on the path to this node. There's 2 leaves below this, namely a suffix of the second string and a suffix of the first string. And you can check there's ABCA and ABCA in those 2 strings. And that's why it has these 2 green numbers, mean there's an occurrence of this path label in the first and in the second string, but not in the third. And well, the third one is not too long. You can check that there is no occurrence of this substring. Okay? So in the tree, without thinking, you can just take what are the dollars that you see at some stage below this node on a path to a leaf. If there's $1 and $2, you find the string that's on the path label towards this node in those 2 strings, but not in the other ones. Similarly, here we have a node that only occurs in the second and third string. And well, in the small example, it turns out all the other internal nodes do have a leaf for each of the 3 strings below them. So let's do one example, the BCA, this one. It has 2, 3, 1, all of them, and actually 2 occurrences in one. So you can find an occurrence in each of the strings. So the structured way to exploit this idea is as follows. You start with the generalized suffix tree. And then at each internal node, you store the subset of the strings that contain this path label by doing a bottom-up traversal of the tree. You walk from the leaves towards the root. Any leaf only occurs in a single string. So by this modified index in the leaf, you know which string it belongs to. So the leaves are clear. They're just the single one. So in our example, this leaf has just the 2 because there's a $2. This leaf has a 1 because there's just $1. And for every internal node, you take the union of your children, and that's it. That way you compute the labels bottom up, and then you know for each node, is there an occurrence of the path label to this node in any of the strings? Next step is compute the string depths, just as before, like for the repeated substrings. And the last step is you walk again through all your nodes a 3rd time. And now you check if this node has the full set of substrings. If every substring occurs below it, then you enter it in the competition. And among all those that enter the competition, you take the one with the largest string depth. OK? So let's try to do this. OK, it's easy enough on the example. Try to answer the question solely based on what you see in the tree, and try not to manually solve it in the strings. Okay, that looks good. I think the table is more helpful than this. A variety of answers. And well, okay, I think the system makes it all, capitalizes all the answers. So BCA is the right answer, which is exactly this node. So the way I wanted you to think about this question is you go through all the nodes. If the node has a 1, 2, 3 next to it, it enters the competition because that means it's representing a string that occurs in all the strings, a substring that occurs in all the strings. And then you look at the little number inside the node that, well, you can read it. And you find the largest such number. That belongs to the node whose path from the root label is a longest common substring. There could be several, but in this case it's unique. It's just BCA. Okay? We have beaten the problem to death. So I hope you agree that if you take the suffix tree or this generalized suffix tree as a black box, this algorithm to compute the longest common substring is not too complicated. It takes a little thinking around corners and getting acquainted to, well, living in these trees. Okay. But the algorithm itself is fairly simple. It fits on one slide, and you can manually do it on an example.